finished percent composition. Just want to do a real quick review of it before we get started with our next concept, empirical formula. We can calculate percent composition from mass data, and here is the formula to do so. You divide the mass of the element by the mass of the compound, multiply by 100%, and that is your percent mass by element. We can also calculate the mass of an element in a compound by using the percent composition. At this point, we assume 1 mole of the compound, and we use the mass of the element in 1 mole divided by the total molar mass of the compound multiplied by 100. Lastly, the other kind we learned to do was calculate the mass of an element in a compound using the percent composition as a conversion factor. So that's your review of percent composition. A few other things we can do with percent composition. First, we need to talk about empirical formulas. Empirical formulas, the empirical formula of a compound gives you the lowest whole number ratio of the atoms or moles of the element in a compound. It may or may not be the same as the molecular formula. Okay? For example, the lowest whole number ratio of hydrogen to oxygen in hydrogen peroxide is 1 to 1. If you'll recall, hydrogen peroxide is H2O2. There are 2 hydrogens and 2 oxygens, and that ratio simplifies to 1 to 1. Okay? So the empirical formula, not the molecular formula, this is the molecular formula right here. The empirical formula is HO. The lowest whole number ratio is 1 to 1. Again, the molecular formula here has twice the number of atoms as the empirical formula. Looking at carbon dioxide, here is the molecular formula, CO2. And the empirical formula for CO2 is also CO2. Okay? That lowest whole number ratio is 1 carbon to 2 oxygens. Right? So again, for some compounds, the empirical formula is the same as the molecular formula. If you recall, do you remember we talked about this ionic compound at one point? It was tin sulfide. But when we did the balancing with the charges, and we did our flip-flop rule, many of you came up with the following. You came up with tin 2, sulfur 4. Remember that? You got a 2 to 4 ratio, which can be simplified to a 1 to 2 ratio, okay? And you end up with 10 sulfide, 10,4 sulfide. And that is in a 1 to 2 relationship. Now, it's not a molecular formula, it's a formula unit, and generally an ionic compound formula unit is going to be an empirical formula. How do we use these? Well, we can solve many equations or many types of problems, but here's a very specific type. It's sample problem 10, sorry about that, it's point 12 on page 331. And we're asked, or we're told that a chemical compound is analyzed and found to contain 25.9% nitrogen, 74% oxygen. What is the empirical formula of the compound? Empirical formulas require a 2-step process. Sorry about this. Trying to get to the right spot here. Well, I guess we'll be starting right here. First thing you need to do is you need to determine how many moles you have. Now let's assume that we have 100 grams of this compound. And if we have 100 grams of this compound, we will have 25.9 grams of nitrogen. And we'll have 74.1 grams of oxygen. Okay? If we had 100. Now, we need to convert that to moles. How do we do that? Well, we're going to multiply by a conversion factor that will give us moles. So it must have moles on top And we need to get this gram right here to cancel, so we don't have grams on bottom. This is starting to look like this conversion factor, a molar mass. The molar mass of nitrogen is 14.0 grams per mole. Grams will cancel, and we'll get the number of moles. Same thing with oxygen. 1 mole of oxygen, 16.0 grams of oxygen. Grams cancel, and we'll be left with moles of oxygen and moles of nitrogen. Solving, we get 1.85 moles of nitrogen and 4.63 moles of oxygen. The next step, we want to divide both of these numbers by the smallest of these two numbers. That smallest number is 1.85. So here's what we do in the second step. We divide 1.85 moles of nitrogen by 1.85. And we also divide 4.63 moles of oxygen, that's what we calculated, by the same 1.85. And now we're going to get some whole number ratios. Sorry. When we divide 1.85 moles of nitrogen by 1.85, we get 1 mole of nitrogen. When we do the same for oxygen, we get 2.5 moles of oxygen. Now let's take these numbers and create a molecular formula, or an empirical formula, I should say. Nitrogen comes first, and there'll be an invisible 1 here. Oxygen comes next, and we have 2.5 moles of that, so we will put a 2.5 here. Now in our formulas, we can't have a fractional or decimal number here, so what do we need to do to this whole, both of these subscripts? We need to multiply them by 2, which would actually give me a 5 here. It actually removes this decimal. And we'll also be multiplying that invisible 1 by 2, and we'll get into 5. That's a subscript 5. Let me write it a little smaller. And that is the empirical formula, dinitrogen pentaoxide. That is the empirical formula for the compound that we were given this percent composition for. And on page 331, you can now do 39 and 40. Now that you've had a chance to complete those, I just want to show you this chart real quick. It's a comparison of empirical and molecular formulas. So first of all, we'll start with CH. There is no molecular formula CH. It wouldn't make sense in covalent bonding. So this is an empirical formula, and its molar mass is 13. Okay, it's an empirical formula. The molecular formulas that are related to that are, if you multiply C by 2 and H by 2, you will get C2H2, which is ethyne. And that is a molecular formula. And you can see right here, we multiply the molar mass by 2. Its molar mass is 26. And multiply by 6, and you get benzene. And its molar mass, benzene, would be 78, which is 6 times 13. So these empirical formulas are kind of like, I guess, mathematical building blocks. Same here, CH2O, that's methanol, which is an actual empirical and molecular formula. There is a methanol, and it has a molar mass of 30. If you multiply all of those by 2, you get ethanoic acid, which is a molecule that has a molar mass of 60, which is 2 times 30. 2 times its empirical formula. And lastly, if you multiply the original empirical formula by 6, you get glucose. And its molecular mass is 180, which is 6 times 30. So that gives you an idea that the empirical formula is kind of a mathematical building block for molecular formulas and molar masses of larger molecules. And here we go. Here's another type of question that we can answer. This is sample problem 10.13 on page 333. We're going to find the molecular formula of a compound using its molar mass and its formula. Here's its formula right here. Okay, so we know that the molar mass is 60 grams per molecule. And my first step is going to be what we've done in the past. I have 1 carbon, I have 4 hydrogens, and I have 1 nitrogen. And if I were to calculate the molar mass of these, and then add them all together to get the molar mass of CH4N, carbon is 12.0 grams, hydrogen would be 4.04 grams, and nitrogen would be 14.0 grams. Our significant figures will be right there. 0, 0, 30 grams per mole. That's the molar mass of CH4N. Now this is the empirical formula, so we have a special name for molar mass of empirical formula. We call it the empirical formula mass. Not the molar mass, but the empirical formula mass. And when we take this molar mass right here, and we divide molar mass by the empirical formula mass, we get a multiplier. That multiplier tells us what we must multiply each of the subscripts in the empirical formula to get the molecular formula. Here we go. Simple when you see it, hard to explain. 60 grams per mole is the molar mass. We're divided by the empirical formula mass that we calculated, which was 30.0 grams per mole, and we get a factor of 2. Now we'll take that 2, and we're going to multiply it by the empirical formula of CH4N. Now when I multiply 2 times all these subscripts, remember there are invisible subscripts there, I'm going to get the following. C2H8N2, and that is the molecular formula of this compound. Okay? Now that you've seen that, you should be able to work page number 41 and 42 on page 333.